Good evening all, and welcome to tonight's TI webinar, technology webinar hosted by Texas Instruments, Australia. We are really excited to bring you Problems Worth Exploring, Episode 3 with Jim Lowe and Peter Fox. So if you're a serial Problems Worth Exploring viewer, welcome again. And if this is your first in the series and you would like to see the previous ones, please visit our TI Australia website. Click on the webinar link on the home page, then the on-demand webinars link, which will lead you to all the previous webinars and the two that Peter and Jim have done previously. My name is John Bayman, and I am your host for this event. I teach mathematics to years 7 to 12 students at O'Loughlin Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. This evening, I'm excited to introduce our first panelist for the night, Mr. Jim Lowe. Jim is a very experienced and knowledgeable maths educator who's always willing to support fellow teachers and students, either in the classroom, through QAMT, at conferences, or at Yummy or Yumi Deadly. Is it Yumi, Jim?
Yumi, yeah. You and me doing pretty man. Yeah.
Thank you. All right, well, thanks for being here this evening, Jim. Our second panelist for the evening is Mr. Peter Fox. Good evening, Peter.
How are you there, John?
I am great. Thanks, my friend. As you can see, Peter now works for TI Australia, but was a maths and physics teacher for 25 years. And I know he is knowledgeable with all forms of TI technology, especially the computer algebra system. Peter, thank you very much for joining us.
Thank you.
I'm looking forward to an activity that I actually did with my class the other day, not to the same degree as this. I'm looking forward to learning a bit about this. And with no further ado, we can see your screen, and it's all yours, my friend.
Well, thank you. So, look, this problem sounds fairly innocuous to start with. That is, we're just tossing some coins, and the question really is the game that we're playing, is it fair? So, I've only got 2 coins here. Our game actually involves 3. Aside from the animation being challenging with 3 coins, the actual focus comes back onto 2, as you'll see later. So here's our problem. Alex and Gustav are playing a coin-tossing game. They each choose a 3-coin sequence, and a single coin is tossed until one of their sequences occurs. So Gustav says, I'd like to win on head, tail, head, and Alex would like to win on tail, tail, head. So when one of those sequences comes up and the coin continues to be tossed until it does, one of those 2 boys will win. So our simple question is this game fair? Now, when I have done this with Year 11 students in the past, most of them say yes, because they say there's a 1 in 8 chance of either one of those 2 events occurring. So, a question to our audience is, what do you think? Is this game fair? So, you'll notice that John, our host there, has sent out a little poll, and we'd like our participants to answer whether or not they think this game is fair. Now, we're not going to record that against your name or anything like that. We're just interested to see what our audience thinks. So, what's the questions coming in like there, John? Are they generally thinking it's a fair game so far?
No, there's not. It's coming up with, no, it's not a fair game.
Well, these people must be suspicious of something. Oh,
well, yeah, I've been obviously suspicious of you. I wonder whether you'd ask that question else. But yeah, we've only got 1 person who's not sure, 2 who say yes, it is, and all the rest are piling on the no.
Well, they might have been to a workshop of mine before. So let's just have a look at some basics to start off with. We've said that Gustav will win with a head and tail head, and Alex will win with tail, tail, head. So we could just start by tossing a coin, and we draw our normal probability tree diagram. So after 2 coin tosses, we can see that down here we've got a head-tail combination, which Gustav would be excited about, and down the very bottom we've got a tail-tail combination for Alex as a chance to win. So if we now run out to the 3rd toss, we can see, just as we would think, out of the 8 possibilities, all equally likely, there's a 1 in 8 chance that Gustav has won the game already, and there's a 1 in 8 chance that Alex has won the game already. So I'm thinking to myself, it looks pretty fair. So let's run it out for one more round of coin tossing. We can see that wherever we've won the game has ceased. But in the event we're in one of these other spots, such as this one here, we're out to a head, a tail, so we've got a combination head, head, tail. So no wins there, but there is here a head, tail, head. That's a Gustav win. Down here we can see that there was a chain of events or a sequence of events, tail, tail, head. Alex has won. And we can cast our eyes down there and see that there's 2 more wins to Alex and 2 more wins to Gustav. So I think some of our audience might be a bit dubious about our experiment so far. We've tossed it 4 times, and so far equal probability of either of these 2 gentlemen winning. So again, I'm thinking, is this game fair? Seems to be okay so far. So let's try a simulation, because we've run out of space on our tree diagram there. Now, if you're doing a coin toss simulation using either a TI-nspire CX or a 84CE, both non-CAS items, then I normally have heads equaling 0 and tails equaling 1, or vice versa, generate a random number, 0 or 1, and just as a heads up, if you wanted one of those lists, then you can automatically determine the total number of tails in a list just by finding out the sum of the list. So that's kind of a cheats way of doing it. Now,
a nice thing with that, Peter.
Yep.
Sorry to butt in, but a nice thing with that, I just in the South Australia and Northern Territory part of the statistics course now has a bit of Bernoulli probability going on in there as well, and they use a lot of obviously the zeros and ones, so that fits quite nicely with students understanding that concept.
That's it, and it's pretty easy to generate those sorts of things in some lists. They're all commands directly accessible on the calculator. So if you're using an Inspire CAS calculator, you can use text on it, and that can be involved in mathematical calculations. Now, I've put my heads and tails in inverted commas because the program that I wrote to do the simulation uses text, because don't forget, H and T could be variables, so they could have a numerical value attached, whereas by putting them in little quotation marks, they're now treated as text. And a nice simple way, which I discovered, is that if you create a coin list, then to generate one of those, rather than putting an if statement in and saying if it's 1 or if it's this, you can just dump that command inside your matrix call up. So if I call up 1, for example, as coin 1, that would be a head, or coin 2 would give me a tail, and so on, or coin random, it will choose one or the other. So we can actually generate a head or tail on the screen from a list. So I'll show you how that's done now on the Inspire, because sometimes it looks a little weird seeing it on a screen. So you'll see there's a few variables in here. This is a document I've prepared earlier, so I have my coin list. So if I choose coin 1, then it just says head, and coin 2 says tail. So if I do coin, random integer between 1 and 2. Now, on this case, you'll know before I had the 0 and 1. Because I'm actually calling up the location in a list, I've got to use 1 and 2. Because if I call up 0, I would say you don't know how you can't, it's outside the array, the matrix, if you like, or the list. So just pressing enter, and it's just calling up a random, a head or a tail, but I don't have to interpret a 0 or a 1. I'm actually seeing the text. So that's just a nice way of generating a coin. And Jim Lowe and I are presenting a session up in Queensland on non-transitive dice. And you can do that in a very similar way, where if you want to bias a die, or apparently nowadays you can still call it a dice. If you want to bias a dice, you can actually store your numbers 1, 2, 3, 4, 5, 6. If you wanted, say, for example, to get rid of the 5, you can have it 1, 2, 3, 4, 6, 6, for example, and then just randomly generate a number 1 to 6 out of that list. So it's a good way to bias stuff. Anyway, so let's have a game. We call this game fair because we're wondering if it is fair. And all that happens is that run through a loop until such time as it sees the sequence. So Alex has won our first game. I just have to press enter, and Gustav's won our second game. So you can keep a tally for me, John. I think we're 1-1 so far. What's that? 2-1.
3-1.
Yeah, and then Alex has got that one. So it's at 3-2 now, isn't it?
Yep.
Now we're in favour of Alex, in favour of Gustav rather. What's that? 4-2.
Yep.
5-2. 5-3. 5-4. Alex is catching up. 5-all. So that's 10 games. That looks pretty fair to me. After 10 games, I think it's fair to say the game's fair. Maybe. And for those that are interested in the coding aspect of it, all I do is we toss the coin twice to begin with, because no one can win in the first two, and then we just check to see if Gustav has got the sequence that we're after, or whether Alex has got the sequence that we're after. And if Gustav has, then G becomes equal to 1 to say Gustav won, or if Alex has got the sequence, A becomes equal to 1. So this is a fairly large way to write the program. Now the reason why I did that is so that if people want to, they can investigate other options. So Alex has got his tail head, and Gustav has got the head head. So if you change the numbers, or the coin tosses in that list, then the program will run with a different version of the simulation, whichever other pattern you want to test against. So far we've looked at it with just a, I guess would say, a single game at a time, and we've displayed the sequence of coin tosses, and we've announced the winner. That's all we did. So game appears fair. We've only had 10 goes. Maybe we need a bit more to decide whether it really is fair. So the next program that I wrote was called Fair More. So we're going to have a look at a little bit more detail in terms of the number of games we're going to simulate. Now this time it doesn't show you the sequence that was generated before a win was declared. It will just tell you how many wins Alex got and how many wins Gustav got. So let's have a look. Again, we want to know, is this game fair? So we go into our variable, and you see there's a few more. Now I've got some other stuff happening here which I'll explain in a minute. So let's try our 10 games. 5 apiece. All those dubious people that thought this was unfair. Still looks pretty reasonable to me. None of these are sort of outside what one would, pardon the pun again, normally expect. So maybe we should try more games. Let's try 20 games. That looks
Peter, the nice thing as well with this, with what you've got here is obviously lots of students are used to using apps or little programs that run this, but actually to be able to look at the sort of the bones of what's going on behind the scenes, the actual coding, and actually even create their own piece of code that does it. That adds an extra dimension, doesn't it? It adds more power to the students and their understanding.
Well, that's it, because the other part of this is we run another series called Problems Worth Coding, and we look at how you actually code these sorts of things. But I think, yeah, as you mentioned, it's not a really complicated program to follow. It gets more complicated by the time I get to the last one, but this is still pretty easy to code, because once you've decided how the game works, then you just stop displaying the results and just record them instead. I think most people would probably look at this now and be a bit concerned that the game looks pretty fair. And there's a few people that said no. So let's try a few more games. So we've tried 20 games. Let's try, say, 100 games. Is that unreasonable? 57 to 43? Or 50 games? Is 31 unreasonable? And this is the thing I like about this problem and why it's worthy of exploration, is once we've played approximately 50 games, if we assume that the game is fair, then a probability close to a half, n's bigger than 30. We can approximate the way that those results would have fallen in a fair game, approximate it to a normal distribution. And what I've done is I've made it so that it actually plots where Alex finished with his 31 games. So if we're actually looking at this and doing a 95% confidence interval, 31 games is actually a rejection. We would have said that that game is unfair. Now, it's possible we've made a mistake. We know that a type 1 error, we accept there's a 5% probability that we're going to reject this game as, and say that it's unfair, even if it is. So let's try it again. We would expect in 5% of cases we would actually reject the game even though it's fair. So let's do another, what did I do last time? 50 trials. Now we know that the 31 was rejected. I wonder if 21 is rejected. Let's have a look. Just inside. So we'd accept the game as being fair. So we'll do it again with another 50 games. And 33, that's going to be, I think that's well and truly out now, isn't it? Yep, it is. It's way off in the tail now. So that's 2 out of the 3 simulations that we've run to say it's unfair. We'll run another one. 31, I think we rejected before. Yes, we did. So we're actually getting a few rejections here. And one more. Yeah, another acceptance. So we're still 50-50 on the accept and reject. So the next part of the mathematics course that we see in our senior mathematics classes, and oh, by the way, before I do that, just a little heads up. The way I set that up, I would really like this to be a standard in our operating system, so we should all vote for this, is being able to reset the window settings. So for example, if I'd done 30 trials, I've created these little window settings myself, min x, max x, and lower and upper. So all I was able to do with the window settings here, although it's not dynamic, it's as close as I can get to it. And I can just type in min x, max x, and they're being calculated automatically. And that's how it was setting up this window dimension. So it was kind of happening behind the scenes, but unfortunately it's not dynamic. You'll notice if I go back to those window settings, all it does is remember the numerical values. It's not actually remembering what I typed in. I'd like it if it was remembering what I typed in as a variable. Anyway, we can continue hoping that that comes along eventually. So let's have a look at a slightly different variation. So let's just go back to our slideshow. Still probably thinking it's reasonably fair. So I introduced a third aspect to this exploration, which is fair data. So we're going to generate some data, and what this does is simulates the nominated quantity of samples and sample size. I think people might realize now that we're looking at central limit theorem. So in other words, if we take a reasonable sample size and we take enough samples, then we would expect it to be normally distributed, and then we can plot the results and compare with what we might predict. All right, and ultimately determine, is the game fair? So we go back to here, and you can see there's a lot more stuff happening in the variable list now, but I need most of them. So let's do 100 samples this time. Now, warning, if you're doing this on the calculator, it doesn't go as fast as a computer. So let's take 100 samples of size 50. And I wanted to see how fast it would go on the computer. And I think you'll see that it zooms along quite quickly. And we're done. Now that takes about 5 times longer on the calculator. So just be wary if you start to take samples of size 200. Just be very wary. All right, so let's have a look at that distribution. Oops, not on one of those. Clicked the wrong one. On a data and statistics page. Now remembering, we were doing 50 games at a time, so we would expect Alex's wins to, on average, be about 25 wins in our 100 samples of size 50, and oh, look at that. We're sitting at around about 30. Now, that's, well, believe it or not, approximately normally distributed. If we took more samples, not necessarily bigger ones, but more samples, that would be better approximated as a normal distribution. So if we look at that as a histogram, the calculator actually then allows us to do a normal plot straight over the top. So we see we get an average of about 31 and a standard deviation about 3.66. And it just so happens I have one just like that. Let's just check. 31.08 and 3.66. So 31 point, was it 08, wasn't it? And 3.66. That's the distribution of Alex's scores. The red one is a distribution that we would expect if the game was fair. And what I like about this, other than the fact that we're now doing a sampling distribution, we've got a good chance to explore what we call type 2 errors. So in other words, if this point that I've just dropped here randomly, if that point belongs to the blue distribution, it's reasonable to expect that it could have landed in here in that blue distribution. However, if you look at its location under what is the assumed or hypothesized distribution, we would have actually accepted that and said that's a reasonable result. So we would accept the hypothesis that the game is fair at a 95% confidence interval, but I can actually tell you, and as you can probably determine from that normal PDF, it's not fair. The two distributions are close, and that's why we've got actually a very large type 2 error. So how do we get rid of a type 2 error? You can't just rub it out. So let's try again 100 samples, but what if we increase our sample size? Now, depending on what the students have done in the past, they will realize that if I increase the sample size, I will reduce the standard deviation. So, but as I said, be wary, because if you're doing this simulation on the Calgano, this one does take a lot longer because we just ramped up the size of each sample to 200. So now I can go, I'm just going to drop another data and statistics page in rather than resetting the window settings. And let's have a look at Alex's result. Now remembering we're playing 100 games in each, 200 games in each sample. So we would have hoped for a mean, if it was a fair game, we would have hoped for a mean of 100. Definitely don't have that here. So again, we can go back to histogram. And we have to do a histogram to do a, a normal distribution under this Analyze menu. So now we have a mean of 124 and a standard deviation of 6.8. So 124 and 6.8. So I can get rid of that one. That was our old one. Delete. And here, and again I've set up the window settings as I mentioned before, where I've got these funny little variables, min x and max x. They're on the assumption that our game is fair though. So that's our distribution if the game was fair. Now we ended up with a mean of 124 and 6.86. So let's just put those in. 124 and 6.8. And now we can see, and I can shuffle that along a little bit, and it's a little bit deceiving here because I've set the scale according to the standard deviation, but if I'd squashed it up, we would actually see that the standard deviation of this distribution is narrower, as in we've squeezed it up a little bit, actually by dividing it by the square root of n. But if nothing else, we can see that we don't have the same size overlap between our two normal distributions, the hypothesized one and the actual distribution, our sampling distribution. And therefore, a point somewhere within that sampling distribution is now less likely to be accepted in the hypothesized distribution. So we've reduced the type 2 error. So, is the game fair? We almost got there before, so let me highlight where we had our coin distribution here, and I'm just going to hide off the first bits because they're no longer relevant once we get to here. We're accepting that that third column in that tree diagram, if you like, is all fair, Everything up to that fourth column is all still fair, but let's just highlight what happens for Gustav right now. So if we're having a look at the last two coin tosses, where can we go for Gustav? He could win here, head, tail. The next one, if it's a head, he could win. And he could win it down here as well, head, tail. If the next one's a head, he's won the game. Now let's have a look at Alex's wins on the other hand. So we've got tail, tail. If the next one's a head, Alex wins. Tail, tail. Next one is a head, Alex wins. And there's another one here and another one here. So in actual fact, if I had the room, inclination and time, we could see that it's starting to favour Alex's wins. And part of that is because the heads in the previous one have dropped off, which means now Gustav hasn't got that head-tail combination kicking off as often as what Alex has his two tails. And just as a spoiler alert, there's the actual distributions or the probabilities for all the different outcomes. So if player 1 chooses head, 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 player 2 chooses tail, head, head, actually gives them a 7-to-1 odds on winning. Head, head, tail, then player 2 can choose tail, head, head, giving them a 3-to-1 odds on of winning. So is the game fair? Certainly is not. In fact, you make sure your opponent chooses first, and there's actually a strategy that you can then do based on their answer to ensure you're going to end up with a much better probability of winning in the long run, of course. Now, I didn't come up with this problem, but what I'd like to show, because otherwise I'll run over time, is that there's a couple of people talk about this and similar problems on the web. One of my favourites, Mind Your Decisions, a guy by the name of Presh Talwalkar, presents some of these things and goes through, as you can see on the screen now, the theoretical calculations that are required to solve the problem. This one he's presenting here is a 2-coin problem, not the 3-coin one. It's a little bit easier to solve. You can see there's some conditional probability. He sets up a couple of equations and then goes on to actually show it in its full solution as simultaneous equations. Another one, which is the whole game, called Penny's problem. I like to drop off the E and call it Penny's problem, as in a coin penny, but that's just my sad sense of humour. Great guy by the name of James Grime, and I just saw on the comment list that one of our participants has seen that one. Under the heading of number file, great if you've got a few months to kill to watch all their videos, because there's some brilliant mathematics on it. So James Grime goes through the actual theory as well. I've only done it from the simulation point of view, but the theory itself is achievable by a student in year 11 or 12, but a good challenging problem. So I can see that I'm about out of time. We're at 7:30, so I'm going to pass over to Jim Lowe.
Thanks, Peter.
Thanks, Peter.
Yeah, welcome.
That's a fascinating problem, that one, and I had an interesting experience with a group of teachers a few weeks ago where we had a little play around with that, and yeah, we used a bag of M&Ms just tipped on the desk and arranged into rows, and used that instead of coins to get a large number of outcomes without having to resort to the technology in that particular case, and caused some interesting results because I, of course, knew the option to choose a desired outcome, and so I always won. So I got lots of M&Ms. Anyway, but it was a great way. It was actually working with teachers, a great way to start a session on probability, because I think that's the whole thing with probability, why we need to investigate that it's not always what you seem. It sort of goes against your intuition in some ways. So to start into my section tonight, Peter was taking our probability from the introductory level with the tree diagrams through to some fairly sophisticated analysis of some concepts at year 11 and 12. I'm going to stay around about year 10 with this problem, but it's actually a problem that requires mathematics way above year 10 in its traditional approach, and calculus and a lot more beyond that. But we're going to take a numerical approach to a classic problem, and that is the problem of curves of quickest descent. So a lot of participants might have seen this one before, but I'm not sure kids have seen it. So this is one of the quirky things that happens in my back patio, that we set this up the other day. And a couple of questions to pose to the student. Which is the shortest path? Well, we know that a straight line between those 2 points, or in this case some 120 millimetre coach screws screwed into this pegboard. The shortest distance is a straight line, and we've actually got a bit of Hot Wheels car racing track mounted on a piece of aluminium angle there to keep it nice and straight. But which path will be quickest? Well, that's what we're going to explore in a moment, because this one is clearly longer. We've got our flexible curve there, and talk a little bit about how we're going to set that up as far as the problem analysis. But let's have a look at the video first of all, and just verify what we, or the result that we're going to use. So some pretty ordinary video capture by my lovely wife, so I'm just going to race ahead here because all the rest of it there is me waving arms around and saying, would you just start the thing, and so forth, right? So we're going to get over there, and we've got the two cars there, an orange one and a blue one, and it doesn't look like it in the way they're arranged there with the angle of the camera, but I was attempting to keep the front wheels level on each track, even though the track was at different angles. So if we just play that for a moment, and we see that the curve path won there. So if you didn't see that, we'll just run that through very slowly, and you see that because of the steeper slope, the car on the curve path starts to race ahead, and you can see that by the time it reaches the finish there, the blue one is still around that join in the two boards that I've got there. So just to verify it for any students or anything like that, because we know that red cars and orange cars and so forth go faster than blue cars, we had to change them around and do it again with the cars, same two cars but on the different tracks. So we've got that happening there, and I'll let it go, and you can see that this time it's the blue car on the outside or the curved track that races ahead and reaches the end, again if I can do it, just about the same distance ahead with the car on the linear track, just about that join in the board. So we've got this, and those that know this, that's a fairly classic curve, and we know that in certain circumstances, not all, but certain circumstances, that path turns out to be a cycloid. And that's normally way above year 10. But we're going to take a numerical approach and pose a few problems for the students to investigate. So one of the things we did, the whole idea of setting this up, as we said, the linear track's mounted on a bit of aluminium angle so that it doesn't bend. This one was actually set up with a bit of clear plastic tubing glued to the track about the middle so that we could just move that point up and down, and so we could get slightly different positions. So we kept it in the middle between the two end points and move it up and down there and pose that, okay, is there a case where the straight track's going to be fastest, or is the curved path going to always win? And is there a point where we get a curved path that is faster than any other curved path that we can come up with there? So we need a way, if we're going to use numerical methods, we need a way of approximating that. So I need to acknowledge that, again, didn't dream up this task myself, but it appeared in a AAMT newsletter as a summary of the things that have been posted on the discussion list for that month, and it was this little article here that is already open, but never mind, it's opened it again. So, yeah, that posed exactly the problem that we've talked about, and then, excuse me, looked at a numerical solution and then wrote some code to investigate that. Now, this code was written in Python, which is another free scripting or coding language that's available out there. But somewhere in this article, the author made the point that it's not really terribly difficult mathematically. The hardest part of doing this was writing the code to display all the points and so forth, which is what gave me the idea, because on the Inspire, we have all of that facility available to us. We've got a graphs window that or a geometry or any of those things where we can display points, and we can read the coordinates from those, and we can have them linked, and we can access those in a program or a spreadsheet or anything like that. So my thinking was that half of this problem, half of the coding problem, the bulk of the coding problem has already been done for us. We just need to do a little bit of mathematics. And that's what we wanted to do. And it gave us this opportunity of exploring a little bit of computational thinking. And so a big part of computational thinking is to break the problem into manageable chunks. And so as far as the students are concerned, really all the mathematics that we have to do in this one is to be able to work out if an object starts at this point here where we know the coordinates and it finishes down here in a straight line path, how long is it going to take? So that's well within Year 10 mathematics. They can use the distance formula to calculate the length of that path, and if they haven't already done it in science, we can do a little bit of work on the equations of motion and so forth in order to work out the time taken for that path. And the little bit of extra that we have to put in there, if they haven't done it already, is to introduce this idea that this thing's falling under the influence of gravity, and the acceleration along that path is determined by the angle that we've got there. And once we've got that, that's all the mathematics they need to explore this problem. So when we do that, we then consider the second option, that we put in one intermediate point between our start point and our end point, and basically use the math that we've already done, but just repeat it in 2 stages. The only difference is that it's starting from rest at that point, then when we get to this point for the second stage, the final speed at the end of this segment is the starting velocity for the one along here. Now, there's a lot of assumptions there. We're assuming that our particle can negotiate that bend without being slowed down and all sorts of things, but that's a discussion to have with the student. So having done that, then a couple of things that we need to mention there, that in order for this to work, we keep this intermediate point with its x-coordinate halfway between our start point and our end point. And the reason for that will become evident by the time we get to the end of the problem. So, having done that, that's where we pose the question for the students. What happens if this intermediate point changes? We're going to keep the x-coordinate halfway, but we're going to move its y-coordinate up and down and see what happens. And that's where we can either do this as a class investigation, and we can give, groups of students or pairs of students different values for this Y coordinate and go and investigate and pull the class data, or we can write some code. Now, we're not going to give all of our participants tonight a task to go away and solve, so we're going to have a look at some code to analyse this. And okay, that should already be open, so let's just find...
Jim, we've just been asked by an attendee, if you were going to do it as an investigation, would you link it with the geometry talk of it, or would you bring it in when you're doing trigonometry?
Look, this is one of those problems that my thinking on this problem has changed constantly while I've been working on it. And I think it's up to any teacher to decide where they're going to use this. When they see the finished result, that might influence them. But, you know, I started out thinking of it as a coding problem, and then I'm thinking, we could write the code and just let the kids play with it and just treat it as an investigation. And certainly the initial calculations I was thinking was things like analytic geometry, letting them use things like the distance formula to come up with a really cool result that you'll see at the end. So I don't know if I really answered that question, but that's my thoughts on it. Is the more I play with this problem, the more I think of different ways I could use it with kids. And unfortunately, one part of my job, or the part of my job now, is that I don't have a class. I'm working at the university, and I go out into schools and work with teachers and so on, and get to work with them in classes, but I don't have a class of my own to really investigate this anymore and see the best solution. So leaving it out to the people up there to pick it up and run with it.
Which is great, and perhaps they can then drop you an email down the line and let you know how it went.
That would be wonderful, because I'd love to hear it. Okay, so in this Inspire file, stage 1, we're just talking about exactly that, and we're explaining all of those things that I just put in the slide, just to sort of speed it up. And we give the students the option to write some code, but they can also just make use of the code. So I think I just need to put so many things open here. Yes, it's part 1. I confused myself with which variable I used for the program. Okay, so what we've got shown up here, we've put in a slider that if you wanted to make the initial velocity something other than 0, you can change it. T and D is the time for the single path between the 2 points, and TT and DD is the 2-stage path. So TT is total time for the 2 stages down here, and DD is the total distance. So what we're actually trying to verify for the kids is that you notice that the total distance along the red path is greater than that, yet the time taken is slightly less than the path along the blue path. And we can allow the students to vary these things and pop down in here to the bottom window and type the program path 1, and you notice that nothing's going to change up here because we haven't changed the initial and end points, but our times here change slightly, but we've still got that situation where the 2-stage path is longer, but the time is still a little bit shorter than this one. And it was set up as an investigation for the kids to be able to move points around and run the program and look at the results. So I need to move a little bit faster here, or we're not going to get to the end of the night. So that was the first stage of the investigation. We then come into the second one where we pose that problem that what happens if we move that point up and down. And that's just a little animation to try and illustrate what it is that we are talking about. And we're going to gather some data on that. And enough of the animation. If we do that, we could use the data capture facilities built into the TInspire, but since I initially started this as a coding exercise, we did it as part of the code, and you will notice that in this one now, again, that point can't move sideways. It's restricted to the midpoint between these two. And we get the code to work out the total time taken for this path, and what we're interested in is this y distance here, this drop from the standard, the change between where it would be if it was on the straight line path to where we've got it there. We've got a pile of data there, and the interesting thing about it is that we get a curve like so. So that would be a whole new investigation that it's taking us into if we wanted to go down the track of trying to fit a curve to that. Would take us into a whole different sort of investigation. But going back to this one, you can see there that we've got a program called path min. So as well as getting the total time for each position, it's actually recording where the minimum time was, so that if I start it there and I do path min and run that, it will work out where that minimum point was. And if I go to this graph and if I put a trace on there and look at that and start to move it around somewhere along there, I think it was about 1.17 or something like that. No, it was actually 1.1. So there we go. Somewhere hitting that window. Whoops. What have I done there? Where did I go? Don't know. Something strange happened there. Let's go back and undo it, and let's do that. So there. So the minimum point on that graph corresponds to the result that kids are seeing here. That would give us the minimum time or the fastest pathway along there. So that's a good result. There's lots of things that we could investigate in there, as we said, but we're trying to just develop this idea of thinking through this problem and chunking it up. And so I'm just going to go back to the PowerPoint for a moment and look at this again. We've done that bit. There's the data. That was all just in case things didn't work tonight. So now we're going to consider multiple intermediate points, and we're going to space them equally between the initial and the final point. And the key to this is that we're still only going to use the procedure that we've already developed. So what we've got there's our start point, there's our end point. We're going to put a number of intermediate points in there, but we're going to do this at one point, intermediate point, end point. That's step one, and we're going to find a way of minimizing the journey from there to there through this point by moving that point down to its minimum. And then the next stage is going to use these 3 points and so forth. So we just use the maths that we've already done, which, remember, used the same maths just for the 2 points. So it's still that find the distance, find the speed, hence find the time, and repeat it all the way through. And that gives us some further bits of analysis, so we can talk about how to find the initial points. We want them equally spaced, so we find the width of each section, calculate the x-coordinates, and teachers would see that we're starting to introduce these kids to some things that they would find if they were, for example, doing numerical methods of integration or something like that with intermediate strips and so forth. So they're getting exposure to this thing, this sort of thinking. Find the equation of the line joining the start and end points, and then find the y coordinates for each of these x coordinates on that line. So that's taking us back into the Year 10 mathematics and so on. And just to reiterate what we've said about this idea that our step 1 would use these 3 points, step 2, next 3, and so on down to the end. Somewhere the label for PN or P4 has disappeared. So if we have a look at that, okay, that's already open. Let's go to it. And we've now got that, all that information's in the TNS file that will be available, so you can go through that one. And in each case, what I ended up, because I changed the thinking, initially wrote it as a coding task, and then I put in the second problem where the code was already written and just leave it for the kids to explore. So if we move these points around and so forth, I can type this program called pathfind1, and that will ask me how many intermediate sections do I want, just so that you can see it change. I'm going to say 4, and it will line them up equally spaced, 4 sections, 3 intermediate points along the line joining our start and end point. So that was the first thing for the kids to do. So that's their Year 10 maths being used there. And then we go on to the final section, and I'm going to skip ahead fairly quickly there because it's there. We've now combined the two things that we're going to find the intermediate points as their starting one, and then we're going to try and minimise the time for those intermediate points. So just to do that, I'm going to run pathfind, and I'm going to say 4 intermediate points so that you can see it, and then I'm going to say pathmin, and it's a variation on the one we had before, so path minimum 1, and do it. And we get that result. Now that's a long way from the classic curve that we had at the start, but of course once we've got that, we can go back to the start and repeat that sequence of 3 points and so on, and run it again, and run it again, and run it again, and so on. And you see that we're starting to get a fairly good approximation to that classic-looking curve. And once we've got that, then the kids can start to investigate by changing the number of points and seeing what happens. So if I just quickly do that before we finish, so if I go, whoops, go back to pathfind, and let's say I put in double the number of points, this time 8 points. Ooh, that's not what I want to do. Run the program first. Pathfind, run it first. Now say you want 8 points. And there we've got that, and let's run this program, and you can see what's going to happen there, and we've got more points, and it will eventually give us that sort of classic curve, and you don't actually have to do too many iterations before we don't get too much movement at all. So we're getting towards an optimum solution. Now, all of the coding for that, I've skipped past the coding, but all of the coding for that is really those initial calculations, distance formula, and the equations of motion, and then we just put them into some loops and repeat them. And it's just a basic for loop, and we repeat it a certain number of times until we do that. Now, I know that that is not giving me exactly the curve that it should be, because there's different situations there that I didn't want to get into with kids at this level. There's the classic cycloid curve only occurs when the slope between the lines is less than a particular value that escapes me at the moment. It's something to do with, I think it's pi over 2 or something like that, the slope, or 2 over pi, I forget. But that wasn't the point of this exercise. We've got something approaching that classic curve. And the interesting thing is that if you decide that, oh, this could lead to, you know, limits perhaps, and we start to stick in a whole lot of points in here, like 50 point or 20 points or something like that, we don't actually get as good a result, because we need this first point to be able to drop down considerably. And if they're too close, with too many points, then the first point's over here somewhere, and we're not going to get that sudden drop that we need to produce that curve. So there it is. That's a bit of an investigation, and as we said, I'm happy for somebody to pick that up and run with it with kids and see how they respond to it and what sort of things they investigate. But it is just that initial calculation of the distance formula. There's the distance formula, there's our velocities, and that's, you know, that's what we use over and over again. So love to see people pick that up and run with it, and I think I should stop there and hand back to you, John.
Thank you, Jim. What I think is fantastic about that, and when we saw it happening with the, when you actually saw it happening with the visual and the video that we had before, that they can actually hang something on what they're doing. So, you know, they're doing the math there, but then they can also link it to, oh, I remember when I did drop that car, and I remember moving that track, and I remember what it was happening. So, and especially with that visual you had with the Inspire screen, it looked exactly like that whiteboard you had in the video, which was fantastic.
And that was my original intention, to let the kids work out some theoretical things and then go back to that peg board and see, you know, if they'd use 4 or 5 points, see if they could peg those as close as they could to those points on there and get that track and see what was happening. Yeah, that was.
Yeah, no.
But as I said, I'm denied the pleasure of having a class to experiment with those things.
Well, I'm sure at report writing time like it is now, Jim, I'm sure there's plenty of people out there that will be more than willing for you to take their class the next week. So perhaps we'll get some emails sent in to you later about that when you get bored there, mate.
The thing, that track was $4 worth of an extension pack. You don't even have to buy whole Hot Wheels. Just buy the replacement pack of 4 bits of track and 2 cars. You know, it's cheap as chips to set up. And I'm sure everybody's like me. It's got bits of board like that lying around in their shed that, you know, you never throw out and so forth. Yeah.
I think the track line was just some excuse that you gave to your wife, actually, Jim. I reckon you got the whole set there somewhere that you play with. Come on now.
No.
Any? No. Anyway, well, thank you for that, Jim. And Peter, that was fantastic and a really informative webinar. So thank you for sharing those ideas and the resources, which we know will be available on the on-demand later, so that we can actually all use them back in the classroom. So we're going to begin wrapping things up now. And if you do have any last-minute questions, please try and get those answered, as I do know that Jim and Peter will be endeavoured to answer them, or we'll equally add them to future webinars. And when you leave the webinar tonight, a brief survey will automatically appear here in your browser. Your feedback guides us as we plan future online events, and we do listen to your feedback, and so we hope you share your thoughts in a post-webinar survey. Importantly for your PD, your certificates of attendance will be emailed to you in the next 48 hours, along with a link to the on-demand and YouTube versions of the video recording, as well as any other relevant documents that Jim and Peter showed you tonight. So after we leave, if you do need some post-webinar follow-up, feel free to phone or email us. We'd love to hear from you. And sadly, that brings us to the end of tonight's webinar. Thank you so much, Jim and Peter, for everything you shared with us tonight. Really appreciate it.
You're welcome, and I see that one of our colleagues in Queensland appreciated my comments. I said I'd volunteer. I think Jim's activity would be brilliant at the water parks, going down some water slides to see if they can figure out which ones are fastest. And somebody in Queensland has said to me, not much point in Melbourne at this time of year, but I'll take that on the chin.
Maybe ice skating instead, that'd be a bit loose.
Peter, but be all right for a Victorian. It's nice and rainy. You'd feel right at home at the moment. Yeah.
They did have a freeze for MND the other day at the MCG sliding down into ice, so it's probably appropriate.
Nice one. Well, perhaps we could get involved next year with that, with the big freeze, and hopefully Jim could add some bit of mathematics to it. It'd be great, Jim. And really, thank you everyone for joining us tonight. We do it for you, for your development, and for you to share with your students. So thank you very much for taking the time in such a busy point in the year to join us. We hope to see you back online soon. So thank you all, and good night.